Today, we will be covering concept 2.1, atomic structure as the basis for life's chemistry, to accompany principles of life, second edition for the AP course with Hillis, Sadava, Hill, and Price. We'll be covering pages 19 through 21 today in your text, so if you will, please, let's go ahead and get turned there so you can follow along. Now, with the atomic structure being basis of all of life's chemistry. Okay, so living and non-living matter is composed of atoms. In chapter 1, we focus primarily on living things, what they are, how we classify them. Okay, so when we look at the structure of an atom, as we just saw on the previous slide, we can see the basic structure. Now, hopefully this is all review, but we should already know that our like charges will repel, your protons will repel protons, your electrons will repel other electrons, and our different charges attract. So those electrons being negative outside will be attracted to the nucleus in the center of the atom. Most atoms are neutral because we have the same number of protons and electrons are present. You can see this diagram at the top of page 19. Okay, so when determining the mass of these, what we see is that they are very, very small. Okay, so scientist named Dalton discovered that the mass of one proton or neutron is 1.7 times 10 to the negative 24 grams. So that's 1.7 with 24 zeros in front of it. The mass of electrons is so tiny that it's usually ignored or negligible. Reading in your text, it's estimated to be about 1/2000th of that mass. So very, very, very small. They're also moving very, very, very fast. So when we look at elements, now an element is going to be a pure substance that contains only one kind of atom. So when we look at living things, typically we find these 6 elements making up the bulk majority. And we see 94 that are total, but these 6 being the primary ones: carbon, hydrogen, oxygen, phosphorus, nitrogen, and sulfur. Okay, so when we need to identify different elements, okay, we can use the atomic number. So the number of protons does identify which element it is. And for the purposes of electrical neutrality, like we said, typically they have the same number of protons and electrons, but we can have atoms that have a different number of electrons, and also ones that have different numbers of protons as well. We'll talk about that later in this course. Now, sometimes we use the atomic mass number. So the mass number is going to be the number of protons plus neutrons. Remember, those are about the same. So typically you will see that being double what the atomic number is. And it's also important to note that it is an average of all of the isotopes. On the right-hand column of page 19, you'll see that an isotope is any variant that has a difference in the number of neutrons. So this first slide that we saw in here, which is repeated here again, is called the Bohr model. And it shows that an atom is pretty much just empty. So this right here is helium, and we have our 2 protons, our 2 neutrons, and 2 electrons right here. Helium is the gas that we put in balloons. So with graduation coming up in May, those balloons you get, this is the gas that is in there. And again, it's important to note that we do pretty much have empty space here. Okay, so Bohr models are very simplified, but because of that, they're useful because they can show how atoms behave. And we're really focusing on the electrons because the electrons are what are going to determine whether a chemical bond will form between atoms and what shape that bond will have. Okay, the behaviors of electrons determine whether a chemical bond will form, its strength and its shape. That is very important as we get into biochemistry later in this unit. Now, as we look at our electrons, we see that our first shell has a maximum of 2, our second shell has a maximum capacity of 8, and our third has a maximum capacity of 18. Okay, oftentimes we will share and sometimes even donate some of these to form chemical bonds. Okay, so all of this leads to what we call the octet rule. So we just saw in figure 2-1 how these shells will fill up. The octet rule states that an atom will lose, gain, or share electrons in order to achieve a stable configuration of 18 electrons in its outermost shell. Okay, when these come together, we call these stable associations molecules. So as you can see here in these outermost shells, these elements want to have 8. So as the oxygen has 6, because of that, it will oftentimes form 2 single bonds or 1 double bond with other atoms. The gas carbon dioxide, for example, is 1 carbon, and it will then turn around and form chemical bonds with 2 oxygens, so a double bond between 2 separate oxygens. So if you will, make sure to answer your review questions, and I will see you guys in class to discuss this further.